Good morning from Dhaka, Bangladesh. This is lecture 4 on atomic structure for A-level chemistry. In this lecture, we will continue, but I just remind that in the third lecture, we discussed about few problems on earlier lectures, and then a set of rules for writing electronic configuration of atoms were discussed. Different convention of writing electronic configuration were mentioned. Electronic configurations of few atoms with different conventions were shown and discussed. In this lecture, I talk about shapes of s and p orbitals, experimental evidence of electronic configurations of atom, ionization energy of elements, periodic table, chemical formulae, and chemical equations. But I do not think that I continue periodic table, maybe a little bit, but then chemical formulae and chemical equations in next lecture. Shapes of orbital, s and p orbitals. You see, the shading indicates, let me take the screen pointer. The shading here indicates the probability of finding electrons is greater than 95%. And this is a circular shape. So s orbital is circular in shape, which has got no directional properties. But p orbitals, we do have directional properties in x-axis, y-axis, and in z-axis. In AS level, only the shapes of the s and p orbitals are taken into account, but the shapes of d and f orbitals are not included in the s level. When we talk about chemistry of transition metals, which is included in the A level only, the shapes of d orbital will be considered at that time. Normally, s and p orbitals in examinations are shown in the bottom, where I showed it, not like these shaded one, but it takes time to do the shaded. That if one writes like this in examination, it is okay. Then we are talking about experimental evidence for the electronic structure of atoms. I do talk about mass spectrophotometer, in which a beam of electrons is used, bombarded in gaseous atoms, turning atoms and molecules into positive ions. These electrons in the beam must have enough energy to knock electrons off atoms and molecules. But if we vary the intensity of the beam, it is possible to measure the minimum amount of energy needed to remove electrons in the atom of an element. These measurements, scientists can predict the electronic structure of atoms. Not only this instrument, but also a spectroscopy can study, which one studied the light given out by atoms when heated in a flame. In practical class, in AS and A level, this is called flame test. The spectroscope shows up a series of bright lights. Here it is shown. See? And this is the electromagnetic spectrum, emission spectrum of hydrogen atom. Heating the atoms gives the energy, which jumps the electron from higher to higher levels. When we withdraw the energy, the electron drops back to normal lower energy level. And this is when the one gets the electromagnetic radiation. And in the visible range, you can see it by our eyes, but for below or above the visible range, spectroscope can determine this. Okay. Now it takes. Now we have to talk about ionization energy, because we can determine ionization energy experimentally, and then from those ionization energy we can predict about the electronic configuration of atoms in elements. What is ionization energy? When energy is given to a gaseous atoms, is first knock out an electron, and that energy is called first ionization energy of the atom. First ionization energy, all ionization energy are always endothermic. The unit of ionization energy is kilojoule per mole. But the equation which can represent this definition I just mentioned, M, symbol of an atom in gaseous state, and then when we convert it into cation, gaseous state also, we release an electron. And that is what is first ionization energy. Similarly, M plus, that is a cation, when in gaseous state, we release another electron from it, and then becomes M2 plus, that is doubly charged cation. And that is what we call second ionization energy. And we go for like third ionization and so forth. Please note, if we write this for a third ionization, it is not correct. We cannot directly go from a gaseous atom to third ionization, third cation, and get 3 electrons out of it. And we don't call it ionization energy. This is not third ionization energy. So for third ionization energy, we write like this in equation. Okay? So we are taking an example of sodium atom, sodium, and then sodium cation in gaseous state, and we get electron out, and therefore they have energy 494 kilojoule per mole. Similarly, second ionization energy for sodium is here. If we knock out all the 11 electrons, that is from first to 11 electrons, the ionization energy ranges from 494 to 158,700 kilojoules per mole. So that we do a plot, and it is difficult to keep this value in one plot. But then if we take log 10 of ionization energy values and draw it versus number of electrons, we can have a graph like this. There it is. You see this graph, and then you can see a jump here, and then you see a jump here. Rest are systematically increasing. These jumps mean that we are going down to a shell. Let's say this is third shell. You can see that this is third shell. And when we go to second shell, that is second shell, we get a jump. Similarly, we go, and when we go to first shell, we get another jump. And this is the indirect evidence of electronic configuration of atoms. What in the right figure show that how easily we can remove the first electron, the last shell, that is third shell. But then it is a bit difficult to remove the electron from the second shell, and it is much more difficult to remove the electron from first shell. Okay, we go then periodic table. We have finished atomic structure. Now we are talking about periodic table. How we develop that's just a history of development of periodic table. Just people are looking for elements, and it is an ongoing process from ancient time. You know, there are few elements in nature. We got it in elemental form. For example, gold. That was discovered thousands of years ago. But because chemistry was not advanced and it was not easier to isolate elements, but in the 19th century, we have enough instrumental facilities. Therefore, it was easy for isolate elements and discover it from the elements occurring compounds. We know we have naturally occurring ores, and from those ores we can isolate elements. You may note also that in 1800 we have only 31 elements. But by 1865, we had 63 elements now. With the advancement of technology in the 20th century, we know about also radioactive elements. At present, we have 118 elements in the periodic table, both non-radioactive, both naturally occurring and radioactive. A nuclear reaction probably in future will be possible to discover new radioactive elements. I can say about how do we distinguish chemical reaction and nuclear reaction. We have shown the valence electron in electronic configuration. So when the valence electrons are rearranged between atoms, we get chemical reactions. So by chemical reactions, we can never get new element. But in nuclear reaction, what we do, we rearrange nucleons, that is neutrons and protons in the nucleus. And thereby, there is a possibilities of getting a new element. So nowadays, it will be always a experimentally determined new elements by nuclear reactions. Well, when we start getting more and more elements, the scientists are thinking, well, we have to have the possibilities of classifying elements in some useful manner. There were some people who even started doing so before Dmitry Mendeleev, a Russian chemist, and Lothar Meyer, a German scientist. But these two are the pioneer of classification of elements in a scheme of all the known elements. What they do, they say the chemical and physical properties of elements are Rekha, periodically arranged in order of increasing atomic weight. Though Mendeleev and Meyer are the pioneer, but Mendeleev was given more credit for advancing his idea. What he did when he arranged elements in his period, he left several blank spaces, saying that some similarities of properties are there, but no elements are discovered. So what he predicted in 1871 a element. He named it as Eka silicon. And then when scientists discovered this germanium, they find exactly almost same properties what Mendeleev predicted. So Mendeleev periodic table, there are vacant some spaces, and later such tables, such elements were discovered. Even then, we see there are some discrepancies in Mendeleev's tables. But fortunately, Henry Moseley, who developed atomic numbers of elements, what he did, using X-ray spectroscopy, in determining atomic numbers of each and every elements. And when one rephrase this, that is chemical and physical properties of elements, very periodically in order of increasing atomic numbers, then all the discrepancies of Mendeleev and Meyer tables were solved. So now we go to a periodic table. Well, you see, if you search for periodic table of elements, you get several versions of periodic table. I do not exactly remember the year, but United Nations declared a year for periodic table, and there were many versions of different type of periodic table in that year. Well, there are periodic table with names, symbols, atomic numbers, atomic weights, and also periodic table with physical properties like melting point, boiling ionization energy, electron affinity, etc. So you can get various version of periodic table. Even there are version of periodic table of some countries of their own language. So here is the periodic table, which is adopted and approved by the International Union of Pure and Applied Chemistry, which we call IUPAC. And now we have to follow this periodic table. All chemists and everybody should follow this periodic table. And I say we have 118 elements yet now, which is named, and their atomic number are determined. And this periodic table, you are seeing that in different colors. And these colors also tell the names of our groups of elements, what it is. For example, this color, which we call alkali metals. This color, it is alkaline earth metals, and so on here. And therefore, the periodic table can be said it has period and group. Horizontal columns are period. And we have 1 to 7 periods in periodic table. Do you see that? 1 to 7 period in periodic tables. And then we have groups. Vertical columns are groups. So this one is group 1, this one is group 2, and so forth and so on, and we get group 18. Okay? So in this periodic table, we have only atomic number and different colors of metals, non-metals, noble gas, halogens, rare earths, element, actinides, etc. Well, there is a very well-known classification of periodic table. The horizontal rows, as I said, are periods. We have 7 periods. Every period ends with a noble gas. So modern periodic table N is, do remember we were talking about this as shell or principal quantum. So we are arranging elements in 7 principal quantum number 7. That's group 1, 2, 3, 4, and 7. There is another way of classifying elements in 4 blocks. We call it S block, P block, D block, and F block. May I go to this one? These are called S block elements. These are called X block elements. So their valence electrons are in S orbital. Valence electron of these elements are in S orbitals. That's why we call it S block elements. If we come to here, this one, these are the P block elements. Similarly, we call the valence electron we will have in P orbitals. Come to here, these all are called D block elements. They are valence electrons in D orbitals. If we come here, these are F block elements, and the valence electrons of these elements are F or are in F orbitals. They are sometimes called lanthanide series and actinide series also. There is lanthanoid series or actinoid series, but sometimes it's called lanthanides also. Or sometimes these are called transition elements. These are S block metals. These are transition elements, and most of them are all solid and metals. Okay, if we go next, I have discussed this, and then we come to here. Well, one can see the energy gap between 1s and 2s shell are much bigger than the energy gap between 2s and 3s shell. And then again, it is the 3s and 4s shell, the energy gap is less than 2s and 3s. And in 4s, we can see that there are almost overlapping between 3d orbital and 3d, 4p orbitals. So as a result, this 4s, 3d, and p orbital. When we fill this, it accounts for d block elements, and it is called also transition elements, as I said. We can notice here also that electronic configuration chromium is like this. But you see that we cannot fill higher energy level orbital, leaving lower energy level. The 4s is lower than that of 3d. Here 4s has got only one electron. So according to our Aufbau principle, it should have 2 electrons. Similarly, in chromium, it should have 2 electrons, but it is like 4s. Why? It is seen experimentally that half-filled d orbitals and full-filled d orbitals are more stable than that of partially filled subshell. So let's take. Well, we know that physical and chemical properties of elements vary periodically when arranged in order of increasing atomic number that we said. So here is the melting point of elements. You can see the melting point increases if we go a period. So melting point, what is melting point then? Melting point is a temperature of a substance when it changes its state from solid to liquid in atmospheric pressure. So we can see that there are periodic variation of elements as our melting point comes up. Similarly, we will have other properties which I will take in the next lecture. That means I will continue properties of elements in periodic table in next lecture, 1 or 2 or 3 slides, and then continue the next topic, which will be in the 5th lecture. Thank you very much for listening to this lecture.